Hey everyone, this is VIC-II Kawari project update number 6. This is my ongoing project to make a replacement for video chips found in the Commodore 64 computers, with some extras that I added just for 8-bit enthusiasts to play around with. Well, it's been nearly 1.5 years since I started this project, and I finally have a completed solution. Here's one I put together myself. I wanted to get to this stage sooner, but unfortunately I made a mistake on my last PCB run, and HDMI wasn't working, but I fixed that problem and now everything is working okay. Before I get into the latest board, I wanted to let you know about a sign-up form that you can fill out to express interest in purchasing one of these and optionally to participate in a beta test. It's not a pre-order, just a way for me to gauge how much interest there is out there. If you sign up, you will get a notification if there is ever a pre-order sale. In the form, you can indicate if you are willing to be a beta tester. I'll pick a few of those people and send an offer to purchase one of my test devices for $130 US plus shipping. I only have a few of these right now, so not everyone will get an offer. I just want to get some of these into hands of real users, so I'm looking for people who can test quite a bit and report back their experiences. If you do get a test device offer, one thing I definitely need more of is testing on PAL systems. I've actually never tried the composite out on a real PAL monitor, so I have no idea if I got that right. It looks okay in my upscaler, which takes PAL video, but for all I know the colors might be completely off on a real CRT. I also don't know if the PAL RF modulator does anything that might make the picture look different. For beta testers, I'll be sending out updates and they'll run a flash utility and make sure it works without bricking the device. I need to get a larger variety of hardware to test on too, like machines with different DRAM timings, for example. And another area that can use some testing is extra features like high-res modes I added. That takes some programming skill and time. I'll point testers to docs I wrote on the extra registers and sample programs. So the general plan is to beta test to start, see how things go, get feedback from the testers, and maybe I'll start a thread about this project on one of the forums. If all goes well, then we could be looking at the first batch of, say, I don't know, 100 devices in January sometime, but I have to work out a few more things to get assembly going. And here's a feature summary. These are the chip models that are supported by the device. You can software select them. I included the old revisions, which have the older Luma levels for composite out. They have 5 Luma levels instead of the 9 that the later revisions had. And keep in mind that the 6567R56A composite output is a lower quality than the 6567R8, and that's because its horizontal frequency is slightly out of range with what some CRTs or TVs expect. And you'll get artifacts that show up on some monitors or TVs, and I get the exact same video quality, the same artifacts from a real genuine chip as I do on my on the Kawari. So just keep in mind that that's just the way that chip actually outputs video. There's an optional hardware switch between NTSC and PAL. There are 3 video output options: DVI over micro HDMI cable, analog RGB that you can hook up to a 1080 or 1084 monitor or VGA monitor, and Luma Chroma for composite output, the regular video output. There's no VSP bug, that's verified with the VSP tool. You have configurable color palettes for each chip model. You have 18-bit RGB and 18-bit Luma phase saturation for composite. But you don't actually have the full color space, the full space for the Luma channel, because the voltage levels can't go too far below blanking level. And I also included an extended register set, like to activate 80 column text mode. There's actually 4 new high-res graphics modes in total. Like I said, 64K of RAM with block copy and fill routines, and I recently added signed and unsigned 16-bit integer math operations for multiply and divide, and that's just to avoid having to loop for multiplication and division algorithms. Okay, so let's talk about installation options. This is my 250407 board, bread bin, and in order to get this installed, you'd need at least one socket, extra socket underneath to give it a little bit more height to clear these components on the right. Otherwise, it just, you can squish them down as best you can, but I don't think it's enough. It kind of bumps into them, so you need at least one more socket there. But if you do have this installed in a bread bin, there's really no good solution to get the HDMI out. Like I think I mentioned before that the assumption is that you would have to remove the shield and possibly also the RF modulator and replace it with one of those smaller ones. Because with this stuff in the way, there's no way that you can get a cable plugged in there. But you would be able to make your own header here for the RGB and get a cable out somehow. Depends on again, if this is installed or not. It's a lot easier because you have the holes to get a cable through. But with that installed, even with the extra socket, there's plenty of room for the case or the keyboard to go on top, and so that works out okay. So moving on to the next board, this is a 250425 board, and this one has a shield, and if we take off the shield here, the orientation is different. And this one, you can get away without putting in an extra socket, like it does plug in there. I think it depends on this capacitor. You kind of have to move it out of the way, but that will insert into there. And you don't necessarily need that extra socket. But it might actually be a good idea to have an extra one in there anyway. In this particular board, there is no RF shield, and I don't know if all of them come without a shield, but if it is there, then you'd probably have to maybe bend it a little bit up here or remove it would be the best option. Now, putting this back on, it is possible to put that on, but you'd have to bend this out of the way, and then this little flap here would have to get bent up, because otherwise it would hit that board here, and you don't want that. But I mean, I personally wouldn't put this in any way. It's kind of useless. It doesn't really help with anything, so I would just take it out. And this is my 64C shortboard, and this will function in a 64C. Like, there's no compatibility issue like there was with the actual chip. You could not put a real 6569 in here. I think it wouldn't work, and if you tried to put one of the 8562s in the bread bins, then I think it would damage it because of the 12-volt pin. But that pin isn't hooked up on this board, so there's no, like, it runs completely off of the 5-volt supply. So you can put this in a 64C board. It will function. However, there's no good way to get this, no convenient way to get this installed. You'd have to have at least an extra socket to clear these components, just like in the bread bin or the first bread bin. But even after you do that, getting this shield back on is next to impossible. So you wouldn't be able to put this shield on. There's just not enough clearance there. However, what I would do is just not put the shield on and print out those 3D print those brackets that you can have on the side, on the left and the right. And that way, when you put in the keyboard, it has something to rest on and screw into, which is what this is doing. Like, the keyboard would screw into here and here. But without that, then your keyboard would start getting pushed in, and you need that support on the left and right side. So I think I'll have to document clearly what the installation options are, so there are no surprises if you do try to install one of these things in these different boards. Some changes since last update. Video RAM can now be 64K or 32K. That makes banking high-res modes possible now. The 320 by 200 and 640 by 200 modes each take up 32K. But that also takes up a lot more space on the FPGA. But in my main variant, which has all the features I wanted, I figured I might as well use the extra space for more memory. So that's what I decided to do. But that's also an option. So flashing, you might be wondering, how do I get updates on this thing? Well, the device can always be programmed through JTAG, but most people won't have a JTAG programmer. The JTAG header will actually be unpopulated on the boards you get. You can always solder on a header yourself, but flashing new versions of the bitstream will actually be done from the 64 itself. I wrote a flash program that will read the new bitstream off of 2 double-sided disks, and I gave the 6510 a way to talk to the SPI flash through the FPGA. And that's the part that kind of pushed me over the limit with the X9. So you run this little flash utility, it detects the flash chip, and then will flash and verify the bitstream in 16K chunks from disk. Obviously, if you use a Pi 1541 or ST2 IEC, that's more convenient than a real drive, but even a real disk drive will still work. It should take less than 10 minutes to flash a new bitstream using 1541 and with a fast loader, which is still much slower than if you had JTAG, but that's just a limitation of the load speeds on the 64. For beta testers, if you do have a JTAG programmer, that's a bonus because you would be able to recover if there is a failure in flashing. Although there is a golden master image on the board, so a flash failure should fall back to that, but you never know. Alright, lock bits. You'll notice some extra jumpers down here in the bottom right of the board. After I wrote the flash program, I realized that I needed some way to prevent a program from either accidentally or intentionally bricking the device. Accidentally is unlikely, but you'd really have to get unlucky with the combination of pokes. I would hope no one would intentionally write a program that would do this, but you never know. So I added 3 jumpers that control access to some functions. So first, if you want to lock the CPU out of all extended features, you can just remove the middle jumper on the PCB. That will make it behave like basically as close as possible to a real chip. Even the config programs won't be able to enable the extended features. If you try to run a config program, you'll just get Kawari not found error message, just like you would on a genuine chip. There's no way to enable extra features with that jumper removed. So if you're not interested in the extended features and you just want to make sure nothing tampers with your flash without your knowledge, just remove that jumper. So second, if you do want the extended features but still want to control flash access, keep jumper 2 in place and keep a jumper on number 1. So in order to allow flash access, you would remove jumper 1 and then put it back after you're done. And since you don't flash very often, you can just keep it on. You don't have to put it back, you can leave it off, but then just be aware that any program could, in theory, erase your flash. And if the flash does get erased, then the only option you have to have is JTAG to restore it. Finally, there's a third jumper that will control whether changes to things like color palette, some video config params, etc. will be saved. Whether they'll be saved. So the thing there I wanted to prevent was some program intentionally or otherwise changing those config options without your knowledge and then persisting them. With this jumper off, the programs will still be able to change the values, like you can see color changes, for example, but a cold boot will always restore your settings because the program won't be able to save them. So those are kind of like safety jumpers. I was kind of paranoid that someone would start injecting code to intentionally brick devices, so that's why those exist. And there are also 2 more jumpers on the right side of the board, and what these do is let you optionally use the motherboard's clock source instead of the onboard oscillator. So these boards have 2 clocks on them, which is why you can switch between NTSC and PAL. But I added the option of using the motherboard's clock because the dot clock signal that reaches the cartridge port actually comes from the motherboard's clock circuit. There are probably only a handful of cartridges that use that pin. Game cartridges don't. But if you happen to have one that does, if you use the onboard oscillator, the system clock will be out of phase with that clock, and it may lead to that cartridge not working, or it's likely to lead it to not working. I have a Wi-Fi modem cartridge that I think does use that pin, and maybe the RU or Super CPU. I'm not really sure. But if you happen to have one and it doesn't work using the default config, then you can simply move that jumper for either of the video standards that your machine is native to, and then it should work fine. And again, this is something that needs some testing with different hardware. So what that means is if your machine is natively NTSC, you should be able to get those special cartridges to work on NTC but not PAL, and then vice versa. If your machine is PAL, you can get those cartridges to work on PAL but not NTSC. I could have modified the board to output the dot clock, but that would require motherboard modification. I just wanted this to be a drop-in, so that was the compromise I made. I also wanted just to make the device be able to work out of the box in either video standard without having to worry about the type of machine you have. So you can of course always use the machine's clock source if it works, and that's up to you when you install it, and hoping that was a decent compromise. Also, someone contacted me a while ago and asked me if it was possible to implement the 6572, which was a PAL-N version primarily used in Argentina. And that is certainly possible, especially with the clock source jumpers now. What you would be able to do is just choose one of the video standards, either PAL or NTSC, and repurpose it for a 6572, and then set the clock source to use the motherboard. The clock is actually slightly different in those machines than NTSC. And that sort of thing can be done in a fork, though. I don't want to make that part of the main branch because I think it kind of gets confusing. So that can be done at some point in the future for sure. I also did some testing on the 1080, 1084S, 1084D monitors. Everything looked good. I just made my own cables and jammed the jumpers into a female header I stuck on the board. Here's one I made for the 1084S. And here's one for the 1084D. The 1084D uses composite sync, and there's an option in the config utility to use the H-sync pin as C-sync. So that worked out pretty well. I'll have instructions in the README for the project, which will show up on GitHub eventually with pin outs and how to wire this up. But you're on your own when it comes to populating the header for RGB. You can use a 90-degree female header or just solder wires directly on the board, but that's up to you. Alright, demos. So I've been starting to play with my own creation a bit. Here is a test program I wrote that uses color cycling to spin a ball. This is actually the same way the Amiga demo worked, by the way. The spin was done entirely through color cycling. Maybe someday I'll make it bounce. And I also made it spin the opposite way on RGB versus composite just to confuse people. And here's another demo program. It's a split screen showing you can have high-res and low-res split screens. You have the option of allowing low-res bad lines while high-res is enabled. So this example, the high-res is revealed and then hidden again. So that could lead to some interesting experiments. Sprites will show up on high-res modes, but there are some caveats that I will have to document. Composite. Here I've hooked up a switch to two composite video sources going to my TV. One is the Kawari and the other is Real64. Then I use the composite settings editor to try and match the look as closely as possible. So I'm switching here between a Real VIC and a Kawari. So even if I don't get the settings exactly right, you can change them, and I'm actually hoping that's one of the things testers can do. Just kind of come up with the best settings for each chip. Each chip has its own color palette that can be saved. Okay, here's something I found interesting, so I thought I would share. The 6569 has a glitch that affects the address that gets read from when the bitmap mode flag gets flipped right before a bitmap data fetch cycle. And what the VIC is doing constantly is grabbing a character pointer, then bitmap data, but the bitmap data fetch depends on the bitmap mode flag, and that can change the address of the bitmap data and how it's interpreted by the pixel sequencer. What happens is the processor changes the BMM flag just before the VIC uses it in the fetch, and this glitch happens specifically when the graphics fetches were accessing RAM, and then due to the BMM flag change, it tries to access character ROM if character ROM is mapped in by the CPU at that address. But it ends up accessing the wrong memory location for one cycle. Now, I knew about this glitch, but it really is quite a useless glitch. I don't think games use it, but some demos use it. For example, there's this demo errata that puts a secret message at the top of the screen that only 6569 users can see because it uses that glitch. And when I come across glitches like this, I usually turn to VIC code to give me some guidance. But when I found the piece of code that was responsible for implementing this glitch, I found this logic. It says, basically, that if the BMM flag has changed, figure out what the address from was, what would have been the full 16-bit address using the previous BMM flag, and figure out what the address to was, the full 16-bit address using the latest BMM flag. And then if the address from is RAM and the address to is character ROM, then the actual address is this mix between high byte of the to and the low byte of the from. So as an example, if the BMM flag was 0, the CPU sets it to 1. Let's say the VIC would have accessed 00FA. If the BMM flag didn't change, the VIC should access 1806 based on some character pointer it has with the new flag, but the VIC actually accesses 18FA, which is a mix between those two. So for one cycle you get a wrong address, then it gets it right from then on. But this only appears to happen on character ROM accesses. Now when I went to try and reproduce this glitch, I realized that there was no way I could reproduce that logic in my core. That's because VIC and other emulators, or even FPGA implementations of whole 64s, they emulate the entire system, so they have a bird's eye view of the whole system. They'd have global knowledge of things like what the actual full 16-bit address would be and whether the character ROM is mapped, etc. But I don't. So the glitch, the true glitch, is something different than what the code to emulate it describes. The VIC doesn't know anything about the system except what's on the input pins. It only has a 14-bit address space for 16K. It has no idea whether it's going to access character ROM or RAM. It just puts an address out on the lines and later reads the data from the bus, and that's it. The other two top bits come from the CIA chip, and the VIC has no visibility into that, and also doesn't even know if the character ROM is enabled. So something else must be going on with this glitch in the real chip. And I searched online, but it's kind of a hard thing to search for, so I didn't come up with anything that described it. So that meant I was going to have to figure out how this glitch actually happens in the real VIC. And if you look at VIC code, they have this comment right above the section that implements this. They say 6569 fetch magic. Fix me proper explanation. When changing from RAM to character ROM fetches, the least significant byte of the fetch address is apparently latched using the mode from the previous cycle, and the upper bits come from the current mode due to ... Okay, so that's great. So someone figured out why this was happening but didn't document it. So I went to the schematic, and here's what I think is going on. The VIC has address lines labeled A0/A8 to A5/A13, and then A6 and 7 for the lower bits, and then A8, 9, and 10, 11 are the upper 4 bits, or the next upper 4 bits. The VIC can address only 16K with 14-bit addresses, but the 14-bit addresses are multiplexed between row and column address strobes. So first it puts out the lower 8 bits on the pins labeled A0, A8 through A5, A13, A6, and A7, and then the RAS strobe falls. That's the row address strobe. Then it puts out the next 6 bits on the same pins, and A6 and A7 are just set high in that case, and then the column address strobe falls. So that's when memory chips have latched the full address. They latch the lower bits when row address strobe falls, and then the upper bits when column address strobe falls. But notice here that the 4 address lines A8 through A11 are wired as the upper 4 bits of the ROM address. And here is his U26, which is a 74LS373, and what that does is it latches the lower 8 bits of the address when RAS falls. So I think what's happening is this. Let's say we're going from BMM 1 to 0, which is bitmap mode to character mode. So the row is set from A0 to A7 for BMM 1. Then RAS falls. Then the LS373 will latch its 8 bits to that A0 to A7 value. Then the column is set, again the same lines, now A0 through A7 for BMM1, then CAS falls. Now DRAM chips have latched those upper bits. But a little later in the cycle, the VIC decides to react to the new BMM value and changes its mind. So those upper address bits change to what the new BMM value wants the address to be. But for RAM, it's too late. The address has already been latched. So nothing that the VIC does after CAS falls will take effect. And actually, the glitch can't happen too soon after CAS falls because that line is delayed to RAM. So the timing has to be right too. But the ROM chips are directly wired to A8 through A10, which are different pins that share the same value, and they will react immediately to the new address. But its lower 8 bits have already been latched to the old address by the 74LS373. And that's why for one cycle we get a mix of upper, lower byte values from the old and new BMM mode flags, but only when character ROM is accessed, which looks bizarre from the outside view. Now I'm sure someone had figured this out a long time ago, but I thought that I would share that in this update because it's a good demonstration that I can't actually cheat like emulators. I actually have to reproduce the same glitch like the real hardware to get things right. And my guess is that even an FPGA implementation of a whole 64 may not actually reproduce this very subtle detail of how the system is connected. I mean, it really doesn't have to. There's no real point. If the outcome is the same, then you'll just sort of simulate the eventual outcome, which is what emulators do. Which is all you really need, but in my case, I don't have the option of doing that. But anyway, I was able to reproduce this glitch in what I think is the same way the glitch actually works in the real hardware, so I was happy with that. So maybe I'll post an update to VIC-II to describe why that happens. So the primary goals of this project, I think, are done. That was replication and compatibility with genuine chips. And they're switchable, so that's done. Secondary goals, I couldn't resist but adding some extras to play around with. Things mostly to enhance existing C64 software, like the 80-column basic mode is a good example. The Novaterm 80-column driver is another good example. I would like to write a GEOS driver for the 640 by 200 video mode and maybe take advantage of the extra RAM as well. Of course, you can also make something new, maybe make a game or use the new video modes just to play around with, but you're still in a C64-ish environment. But I feel that's done too, and that's why this is going out for beta testing. I'm sure there are going to be some more issues discovered through beta testing, but I'm considering this pretty much done at this point. But if you're like me and you think about, other project ideas, if someone is up for the challenge, here's a big one. You could turn the 64 into a completely different 8-bit machine if you wanted to. You could have a new video chip and processor on this board. It doesn't have to be compatible with the VIC. You can throw in whatever you want in there. Add another processor inside the FPGA. You can keep the 6510 stunned until it's needed to, say, switch DRAM banks or read I/O. And then the combination of DRAM plus dual port video RAM on the FPGA, you'd have a total of 128K. And Kawari can actually write to DRAM. I've never tried that, but in theory it can work. So if you think about it, you could architect a whole new machine. You already have a keyboard, power supply, ports, and peripherals, and you have a sound chip. And you could turn the 6510 into sort of a slave CPU, and then on this board put in your own video chip, another CPU. Your kernel would get loaded from flash. It doesn't even have to be a 64K kernel. It could be much larger because there's actually 1 megabyte of flash space on that chip. And like I said before, I use the 6510 kind of as a slave processor to do I/O or DRAM bank switching, because the upper 2 bits for the VIC are controlled by the CIA port. And yeah, a combination of 64K DRAM and sort of the 64K fast VRAM. And so the CPU would actually execute instructions from the fast VRAM. So it kind of turns the 64 inside out. You would implement your own kernel and CPU inside that Kawari board. And that's just an idea. It's not something that I plan on doing, but it's just a project idea for somebody else if they're feeling ambitious. It's just an idea that I started to think about. Here are some other ideas for forks. They're less ambitious. I won't go through each one, but like one of them is there are certain illegal video modes that the 64 has. You could turn those into valid modes and still maintain compatibility with C64. And like I said, I think I might try the GEOS driver for new high-res modes. All right, this has been a long video. Thanks for your patience. I know people have been waiting for this to get out there. Hopefully things will go well with beta testing. Thanks to my Patreons for their support, and thanks for watching.